Last time we were describing what happens in quantum gravity at one loop, actually. In particular, this was the correction to the chi propagator. So gravity is described by a triplet of fields. One is the metric, g mu nu. Then there is a scalar phi and a spin 2 massive field chi mu nu. And you can express the higher derivative action in an equivalent non-higher derivative way by introducing those fields explicitly. So you will have the Hilbert term, a normal, more or less, action for the scalar field with a positive coefficient because zeta is a positive constant, and a spin 2, massive spin 2 Pauli fields action with a negative coefficient in front, then non-minimal couplings, and then vertices with 3 or more chi's. The connection between the two is obtained by means of first introducing auxiliary fields and then making some changes of variables that are quite simple. However, there is one thing to say, that here the renormalizability of the theory is evident. We proved it by means of power counting. Here it is absolutely not evident because there are infinitely many terms, but general theorems tell you that when you make a change of variables, change of field variables, the theory remains renormalizable. So no matter what you may expect by looking at this action, it is renormalizable because it is just a change of variables of a manifestly renormalizable action. So that means that, for example, this kind of potential containing all powers of phi, when you compute the divergent parts of all the diagrams with an arbitrary number of external phi legs, they will miraculously, all the divergent parts, they will be miraculously connected to one another and fit into the same potential with just a renormalization of k, a constant in front, the overall constant here, and the other constants, which are 1, 2, 3, and 4. So there are only 4 constants here. There are 5, but one is redundant. K squared is like h bar. So let's say there are 4. And here we have set the cosmological constant to 0. Cosmological constant cannot be set to 0 compatibly with renormalization. So even if you set it to 0, renormalization will turn it on again. But that's only to simplify the arguments we are making. You can find in my papers the complete formulas, but the moral of the story will be the same, so there is no point in insisting on that. So the spin 2 field has to be quantized as a fake particle because of the minus sign here, and the scalar field can be quantized the way you like. And that said, you can make all sorts of computations you are used to make in the standard model, because this theory is defined perturbatively by means of Feynman diagrams, and it is perturbatively unitary and renormalizable, like the standard model. So in particular, we were commenting on the correction to the 2-point function of the scalar field chi mu nu, and that means that you have to resum a geometric series like that. I don't know if you saw something like that in other courses, but anyway, this is a geometric series, and it gives you what is known as dressed propagator. The dress propagator means that you have a correction there, so that correction may change the position of the pole, and this is the form of the corrected propagator around the new pole. So you have to find where the real part, because there is an imaginary part here, and the imaginary part is necessary precisely to have unitarity, because remember that unitarity tells you that the imaginary part of a diagram is some cross-section. So in general, the imaginary part of a diagram is non-zero. It's non-zero anytime the diagram can be cut and the particles propagating in the cut are physical. Fake particles do not contribute to the imaginary part, but in general, here you can have any kind of particle, because gravity can be coupled to the standard model in a very straightforward way. Just add the standard model action here, covariantized, and that's it. So this is renormalizable in unitary theory of all four forces of nature. And so when you have the standard model, there will be a redefinition of the metric inside this action here, because the metric here and here is not the same. There is a change of variables, but anyway, let me say plus S standard model prime. Anyway, this is all only technical part. What's important is that you can make the computations as usual, and there will be vertices connecting the metric of phi or chi mu to standard model particles. So here you can have the electron, you can have anything. You can have phi, g mu nu, and chi mu nu themselves. So all of them, you have to take into account of all of them, and sum every contribution, and that gives you this shorthand notation for the bubble diagram, which is actually a sum of many bubble diagrams. And in the end, you compute this thing around the new pole, so you look for the position of the new mass and bar where the real part of this denominator vanishes, and then you expand around that real part, and you will have something like a coefficient in front, because the coefficient will not be 1 any longer. It will be something that you call z. You will have a new mass, of course, and then you will have possibly an imaginary part. So this is the general form of the dress propagator, which gives the Breit-Wigner formula in the static case. By the way, there is no gamma here. The correct formula is that the Fourier transform I've written is the Fourier transform of this expression. So how do we get from there to there? You just, or actually to a constant times that, you just write the propagator, the dress propagator, in the static case. So we will get, strictly speaking, to this thing, because the mass is modified. And so in the static case, if you have a massive particle, you can ask yourself what happens in the reference frame where the massive particle is at rest. So particle at rest, not static case. Sorry, it's not a static case, it's totally not static. It's the particle at rest. That means that P will be equal to some energy 0. If you want a non-relativistic limit, the energy will be the mass at the pole where you do have your particle. But this is a propagator, so it describes virtual particles as well. But let's study the case where, if you want the non-relativistic limit, we have the particle at rest on the pole, if you want. So that will be equal to z divided by e squared minus m bar squared plus I m bar gamma. Or you can also write it like this. For gamma much smaller than the mass. Gamma is originated by the radiative corrections, the bubble diagram, and so it is perturbative if you want. But when we are resumming the geometric series, we are already in a, if you want, beyond perturbative regime. But let's still assume that the width is much smaller than m bar, which is what is normally done. And so you can write this as E minus m plus I gamma divided by 2, E minus plus m minus I gamma divided by 2, and that will be divided by 2m minus I gamma. Apart from the constants in front, you have the Breit-Wigner formula for the particle, and of course the antiparticle, because we are taking the non-relativistic limit of a relativistic quantum field theory, and so we get both. But if we focus on this thing and we study its Fourier transform, we get this result. So this is the Fourier transform Breit-Wigner certain G BW of T. And to study its effects, so this calculation I will not make, but you can just compute the Fourier transform. You have one pole, so the residue theorem is very simple to apply here. And you will have to close the contour, the integration path, above or below, depending on the sign of the imaginary part, gamma, which is what gives you a theta of plus t or a theta of minus t. And how can you use this thing like a generic Green function or like the propagator if you want, but since we are in the non-relativistic limit, it is somewhat easier. We have a convolution between this Green function and a source, whatever it is, and that will give you the response. How the source generates, for example, it could be a field phi, turn on a source that generates like a charge distribution generating an electric field, matter distribution generating the gravitational field. What's important here is that when we replace the solution, the sign of t is not important, but the rest is, the theta function in particular is, so we have the sign of t minus t prime, then we have theta of gamma times t minus t prime, then we have E minus I m bar minus I gamma divided by 2 minus I is a minus. Okay, it's important to have the right signs here and there. E to the minus gamma t divided by 2, so that is t minus t prime, and then there will be the source j of t prime. So we have two cases. One is when gamma is positive and one when gamma is negative. When gamma is positive, theta of gamma, t minus t prime, is theta of t minus t prime. That means that t prime is smaller than t. So that cuts the integral from minus infinity to t. Okay. E to the minus I m bar minus I gamma divided by 2 t minus t prime j t prime. Let's recall that the gamma part, which is the real part in the exponent, is minus gamma divided by 2 t minus t prime and since t minus t prime is always positive, that's a damping factor. So it is a convergent factor, and the important thing is that t prime is shorter than t, which means that your response at t depends only on the source at earlier times, so it depends only on the past. But when gamma is negative, the opposite happens, and this is theta of t prime minus t. So t prime has to be larger than t, and this cuts the integral from t to plus infinity. Okay, the sign there, the sign was positive, so we could take that out. And in the other case, it is negative, so we just put a minus sign, which is irrelevant for our discussion, but we just put it. Let's separate the phase from minus gamma divided by 2 t minus t prime j t prime. And we see that again, this is a damping factor because t prime is always larger than t, and so the integral for t prime going to plus infinity is convergent because gamma is negative. So you have plus, minus, minus, you have plus gamma t prime, but for t prime going to plus infinity, the integral is convergent because gamma is negative, and before it was convergent for t prime going to minus infinity because gamma was positive. But now we have to go to the future, so that means that you need to build this integral, which is the response, any kind of response you want to compute to your source, you need to know the source in the future. But you don't need to know the source a lot in the future, and you didn't need to know the source a lot in the past. Why? Because of the damping factor, which is an exponential that tells you that after a short time, 1 over gamma, this kills everything. But even if you didn't have the damping factor, you just had an oscillating factor in front. So even if you kill the width and you say that your particle has a life equal to infinity, that doesn't change the situation very much because you still have to convolute your source with a strongly oscillating factor, which averages every effect from the future away unless you are able to grab what occurs at such short distance times as to make this exponential factor of order 1. So if m bar, which could be the mass of this spin 2 field chi, is not even necessarily around the Planck mass. Let's assume it's much smaller than the Planck mass. Let's assume it's 10 to the 12 GeV. then you need, so the effect of the future on the past, on the present, is restricted to this kind of time interval, which is 1 over m bar, and that is equal to 10 to the minus 26, 10 to the minus 36 seconds. So 1 divided by the Planck mass, you might remember, is 1 divided by the Planck mass is something like 10 to the minus 43 seconds. Here we are 7 orders of magnitude below the Planck mass, which is 10 to the 12, 10 to the 19 GeV. And that means that you have 10 to the minus 36 seconds. There is a short time interval that you cannot hope to measure. Let me tell you what time intervals we have been able to measure so far. The time interval we have been able to measure is the attosecond. And so let me first complete this sentence. Then you need this to appreciate the violation of causality. So there is no event we have ever been able to observe, that is, no two events that are separated by that amount of time. That's far below what we could measure so far, which is around the attosecond. The attosecond is, if I remember correctly, 10 to the minus 18 seconds. And then if you want indirect measurements of short amount of times, you could go to this here, this graph here, because this is precisely the squared modulus of a Breit-Wigner. And so basically this size here is 1 over gamma, the width of the Z boson, and that is measured very precisely. And if you want to talk about lifetime of the Z boson or the Higgs field, that's not measured equally precisely, but it's around 10 to the minus 25 seconds. So these widths are around 10 to the minus 25 seconds. It's too short to have them reach detectors, for example, because, well, you could boost it with a Lorentz transformation, but if it is produced by colliding E plus E minus from opposite sides, basically Z is more or less at rest, so you don't have a lot of boost here. And 10 to the minus 25 seconds can be derived indirectly from this graph, but it's not really a time interval that's measured directly. And well, here it could be 10 to the minus 36 seconds. If it is, the mass is closer to the Planck mass, it could be 10 to the minus 43. Well, there is nothing you can do about those things, those kind of times. Everything that is separated by longer amount of times is washed out by this hugely rapidly oscillating factor. So that is an effect of a negative gamma, if you want, that talks to the future, but we will see in a moment that you don't really need a negative gamma to have a violation of microcausality. Every time you quantize a particle with a fake procedure, you will have it. Let's check first the optical theorem with this kind of dressed propagator. That's kind of interesting. So let me remind you that what the optical theorem says. Here it is. Okay, this is the bubble version of the optical theorem. We have a non-bubble version, which is this one. This object should be non-negative. Let's check what it is in the case of the dressed propagator. So this object is equal to what? Well, there is a 2. The propagator is I times what I wrote before, times that. So there is a 2, imaginary part of what? There is a minus I, because there is a minus I there. There is an I for the propagator. There is an I for each vertex, or actually the vertices have minus I, if you want. It doesn't change anything. Times the propagator. So we have to compute this imaginary part. What is it? Z is real, because the imaginary part is all contained in what you call the width. At the pole, it is real, general. Minus I times I, and there's a minus sign there, minus 2z, imaginary part of that. So imaginary part of that is 1 divided by 2I, p squared minus m squared plus I m bar gamma, minus complex conjugate, p squared minus m bar squared bar, minus I m bar gamma. Well, the 2 will go away anyway, so that is IZ. Common denominator is p squared minus m bar squared squared plus m bar squared gamma squared. And then you have minus 2I m bar gamma. Let's clean the result a little bit. 2 m bar gamma z p squared minus m bar squared squared plus m bar gamma squared gamma squared. So that should be positive. That means that gamma is positive. The width of a normal particle has to be positive, which means that it has a lifetime. But if we instead put a minus sign in front of the propagator, so if we put a minus sign because we start from minus 1 over p squared minus m squared, as in the case of the fake particle, and we then quantize it like a fake particle, the minus sign will give a plus there, So you will have a plus or minus, and that means, let me separate the two cases by calling gamma plus or gamma minus. That if the residue of the propagator you start with is positive, the width is positive, and if the residue of the propagator you start with is negative, then the width is negative, just to have the optical theorem. That's why gamma of chi is negative. Instead, gamma of phi is positive because its starting action has a positive coefficient. It doesn't mean that phi is a physical particle if it has a positive gamma. It could be a fake one. And why? Because let's see what happens if we now take this propagator, this imaginary part, and take the limit in which gamma, since gamma is a perturbative effect, it is given by radiative corrections, why not study back the limit where gamma goes to 0, which means 0 plus or 0 minus. Well, you know how to compute the limit of this thing, or actually this thing, that's a delta function, probably, but it will be a delta function with, to imagine that this is epsilon, epsilon squared, and then you have an epsilon there, and the result will be plus or minus a delta function depending on the sign of epsilon, because epsilon could be positive or negative. And that plus or minus cancels this plus or minus. And so in total you will always have a plus. There is a z, there is a 2, not sure about the 2. If the 2 should be there or what. Yeah, 2 should be there. We get two z delta of p squared minus m bar squared. Positive, correctly, because it has always to be positive, so there is no chance. But here is a funny thing. If you let this thing decay, for example, you have this, you produce, let's say, this fake particle, and then you resum its width, which means that you let it decay into other particles, as it is done at CERN, by the way. And even if the width is so small that it could be assumed to be a particle that lives for infinity, you would get the same thing as you normally get with a true particle. That's why it is a fake particle, because if you let it decay into anything, it will simulate a true particle. What you cannot do is that catch it on the fly, namely observe chi. But if you observe everything else that into which chi decays, and you resum those things, and even if there is a discontinuity and non-analyticity here, because we know that fake quantization of a fake particle leads to a non-analyticity, then you will have the illusion of an existing particle with the correct plus sign in front. So that is the limit of the peak the imaginary part actually, but you can imagine that when gamma goes to 0, this peak raises to infinity because the height of the peak is 1 over gamma. Yeah, what is the height of the peak? When E is equal to m, you have 1 over gamma. So the height of the peak is 1 over gamma. 1 over gamma. So like a delta function, it shrinks and it goes up to infinity. Well, this is not the imaginary part. This is the square modulus, so it will not get to a delta, but the imaginary part will get to a delta. And so the difference between a muon, for example, and this is that a muon is something you can observe directly because it lives long enough to be revealed by our detectors, but no field like the Z bosons, the W bosons, the Higgs field, they are too short-lived, and this 10 to the minus 25 seconds, that's more or less their lifetime, doesn't allow us to see them. So you study this kind of processes where they are created and they die immediately thereafter, here. And the same for the Higgs. So everything we see in accelerators about these particles are from their decay products, and that's why you cannot distinguish a fake particle and a true one. But as we said the other time, you can distinguish them because radiative corrections, loop corrections, will have different imaginary parts, and the imaginary parts contribute only above certain thresholds, so you have to look for those. It's a long way to go, perhaps, but we have this kind of example. For example, you see this thing that begins at 160 GeV, which is exactly twice the mass of the W boson. That is the process. The imaginary part of that process has a threshold, and it starts contributing only from that. That's one way to get the mass of the W, for example, because the threshold is the sum of the mass of the two things propagating in the middle. It's kind of precise because the mass of the W is about 80 GeV. And so again, if you consider the other process which was missed by lab 2, where Z and H propagate in between, that would have the imaginary part a threshold of 216 GeV. So even if you do not detect either Z or H directly, indirectly you can check whether it is fake or not, because there will be a different contribution above that threshold to the imaginary part. But another important or striking thing is that these effects, many effects, which have a quantum origin because they are generated by the quantization prescription, they do survive the classical limit. They are still small effects, so they have it would not be easy to detect them, maybe, but they do change classical physics, not just physics at the quantum level. And why is that? The reason is that, as we said the other time, to have the unitarity, you have to project these fake things away from the physical space. And that means that this classical theory cannot be the right classical theory, because it contains too much. It contains some things that have to be projected away. So the quantum theory is obtained by quantizing this classical theory, which is local, or this one, this is equivalent. Then you work out the S matrix elements. You can embed all Feynman diagrams in the so-called quantum effective action. But the point is that when you take the classical limit, which is focusing on 3 diagrams only, you will not get back this action because of the projection. The projection will go back to a projected classical action. So basically what you have to do for the classical limit only 3 diagrams without fake particles as external legs. So not all 3 diagrams, because that is the unprojected theory, and the set of the 3 diagrams, all 3 diagrams, is the classical action you start with, by definition. It's the set of Feynman rules you get from that. But if you restrict to the diagrams that do not have phacons on the external legs, then you get another action. And that is equivalent to integrate out the phacons, but at the classical level it is equivalent to solve their field equations. Well, we have something to specify about this, because when you solve the field equations of a particle, you have to introduce initial conditions, for example, position and velocity. And for the fake particle, you don't have initial conditions. That's the point, because everything is given already by the prescription, the quantization prescription. And that's why that integrating them out or not, solving their field equations or not, will not change anything as far as the amount of degrees of freedom is concerned, because they are not among the degrees of freedom. So at the quantum level, they are not among the asymptotic states, and the classical level, they are not in the final, classical action. And that we can see what their green function at the classical limit is, we can see by taking their propagator, which is this one, with a plus or minus in front depending on the 2 cases. We have 2 possibilities. This is the classical green function. So that means that you have to solve the classical field equations with this green function. What is it? Now we will compute it later. it is this thing with the limit epsilon going to 0. We saw the other time that the limit is kind of delicate inside Feynman diagrams because you have to make a procedure to deform contours and everything, deform integration domains, which is in the end equivalent to this average of analytic continuations. But the good news is that in the classical limit you don't need that because there is no integral on loop energies. So there are only 3-level diagrams, so you can take it as it is. That's the green function of the classical limit, and we will see how the violation of microcausality enters there, because this is the sum of the advanced and retarded potentials. So this is not the retarded potentials, it's a sum of the advanced and the retarded potentials. As you see, it is symmetric with respect to past and future, and so you will have a contribution from the future for very, very small amounts of future, so something not yet observable, but it is there. So we will continue in 10 minutes.